Hey everybody, this is Larry. This is day 27 of November Leetcode Daily Challenge. Almost to the end, yay! A couple more days. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, Partition Leetcode subset sum. To be honest, I am not looking at the problem right now, but given the title, I'm guessing some sort of knapsacky dynamic programming, but let's see. Given a non-empty array nums contain only positive fine if the array can... Okay. That's kind of funny because this it's funny because I feel like a long time ago when I started doing competitive programming type things, this is maybe like 20 years ago now. This is probably like a considered maybe not a easy problem, or sorry, not a hard problem, but still a kind of a hard problem because people were not very good at dynamic programming at the time. Some of it is because of a lot of practice that people get to do nowadays that just wasn't available back then. Anyway, without the history aside, so this is actually exactly what I said, which is I want to say it's called knapsack, but it's not really knapsack. I think I mischaracterized it a little bit. It's the zero sum dynamic programming, and there used to be different ways of doing it. But now there are also other ways of doing it. So, things do get a little bit better as different languages. So maybe I'll go over a couple of those as a result. But the key observation for this one, sorry, it took too long to get to the explanation. The key observation to make this one, and it's kind of tricky, is just noting that, okay, so you have to use every number in this array, right? So using every number in this array, the total of every number in this array is just some sum, say k, and then the problem becomes, can a subset of these numbers sum to k over 2, right? So that they kind of cancel out, and that's pretty much it. There are a couple of ways to implement it. But that's the way that I think is the easiest. You can also play around with positive and negative numbers and then try to get to 0. But that's the way that I think I'm gonna attack this problem. Usually for this, then you have to look at constraints, and for here, n is less than 200, and then the sum is, or sorry, each number can be at most 100, meaning that the total of all the array elements is going to be 20,000, because it's just 200 times 100, so it's 20,000, and half of that is 10,000. So you're trying to see if the sum of the numbers, some subset of numbers, could be up to 10,000. And here we can use any number of elements on the left or the right, so it doesn't have, so you don't have any constraints around that. So that's pretty much how I think about it. In terms of complexity, which we'll go over again in more details later after I write out the code, because I find it easier to show it that way. This is actually called pseudopolynomial because your the input, or the complexity is based on n, which is the size of the input, and also the properties of the elements themselves, right? Because if, for example, each element could be a million or a billion, then it's not going to be fast enough. So it's pseudo-polynomial because there is a polynomial component, but there's also a component that is depending on the constraints as well, of the nature of the numbers. But okay, but all that said, this is now pretty much a textbook problem, and what I mean by that is just that is a problem that you may see in a textbook. So I'm going to start implementing. I hope that this is good enough for you to get started. If not, leave me in the comments. Let me know how much more to explain before going to code, because I'm still trying to find that balance sometimes for different problems. But yeah, but now, how would I think about this, right? So, so there are a couple of ways to do it. I think the canonical way is doing it dynamic programming, which is bottoms up. I'm actually, I think that way is good. Once you get to a certain level, it'll be okay. But I think for me, yeah, I mean, I think I'm going. I struggle a little bit to kind of because 20,000 times 100 is about what 2 million. So this may be a little bit too slow to do it top down. But I'm gonna try it a little bit, and then we could, if it doesn't work, we'll optimize it to the bottoms up. It is cutting it close, to be honest, but I'm gonna do it top down with dynamic programming or with memorization. So basically, the question is then, right? Is okay. So the question I would say is now basically, because each number can only be used once or not, we can redescribe the problem as just a suffix of the array, so that because each number is independent of each other, so there's no so we don't have to care that much about it, right? So from that, we're just going to keep track of the index of the value. So I'm gonna can partition, maybe another name. I would only say can partition, but let's just say can p for short. So then now we care about the index and then the current sum or current total, or maybe total left, say. And okay, and now let's just say n is equal to the length of the nums. If index is equal to n, then we're done. So this is false. Well, okay, let's if total left is equal to 0, then this is true, because that means that we reach 0. And yeah, to kind of let me step back for a second, because the base case doesn't really make sense without asking the right question. And the right question here is, given an array of num sub index ... to all the way to the n, basically the suffix of the array, can we reach exactly the sum of total left, right? And if we were able to get to 0, then that means it's true. And if we get to the end and we still haven't reached 0, then this is false, because that means you ran out of numbers, right? So now for each index, we ask ourselves, okay, do we use this number or not, right? So then there are only two possibilities, right? Which is we use this number, so index plus 1, so total left minus num sub index, because we use this number. We have to do some additional checking, but I'm just sketching the outline. Or we index plus 1, total left by itself, because we don't use this number, right? So can we do it? My variable names are always kind of weird, but possible if used, say, and then here we could call it possible if not used, and then at the end it's just return possible if used or possible if not used. And if you're really observational, you may notice that this is actually slightly suboptimal, because there's no early termination. But for the purpose of learning, let's just stick with this for now. And then now the question to ask yourself now, given that this framework, is that now we return can p from the index of 0, and also what is the total left, right? What we said is just half of the total, so let's just say total half, and then now we go through it. Total is equal to the sum of the nums. That's just the total of the array, which we talked about, and total half is equal to total divided by 2. It has to be, and of course it has to be even, right? So if total mod 2 is equal to 1, that means it's an odd number. We could return false. Otherwise we do this thing, and this should be good enough. Other than that, it may be too slow, but let's run it for small test cases to see it's right, and then we'll rephrase this a little bit. Yeah, so this looks good. The timing is 60 seconds. Let's choose a bigger n, because n is up to 200. I like to do that to show memorization and how it scales, but you just copy and paste this, because I think it doesn't really matter that much in terms of things. And if we run the code, it'll either be probably too slow. Yeah, it's gonna give me time limit exceeded, and that is expected. So how do we fix this, right? Well, we do something called memorization. The note is that for every input to can p, it gives you a deterministic answer, right? So every input gives you the same output. So that means that we can actually cache it somewhere. So that's what we're going to do. So now let's just for laziness, I'm going to put this in a dictionary. And you could do this in a number of ways, but and in fact, if you watch my video enough, I do this in a number of ways. But today I'm doing a little bit lazy, so I'm just going to do this way. Let me know about what you think. Oh, I have to check something, which is that if total left is less than 0, we could return false. This is just for early termination. It's not really necessary, but it just makes the code run faster because once you go over 0, or once you go under 0, you can't really go over it again, right? Because we're always subtracting numbers. So that's just a really minor optimization. But yeah, if index total left, this is in a tuple. If this is in cache, we just return cache of this thing. Otherwise, yeah, and otherwise we also cache it later on. Is equal to this thing. And then we can just return this cache. I actually usually write this a different way if you're familiar with my videos, but today I'm feeling a little bit tired, so but we'll go over it. Yeah, so this looks good. I mean, it runs really quickly, right? I don't even know what end this is. I mean, there's a lot, but yeah. So the worst case scenario, we should test that a little bit because that is the thing that we worry about. But we'll go over the complexity of this real quick, which is what is the complexity of this, right? Well, what is the number of possible inputs to this, right? So the number of possible inputs index just 0 to n, and total left, this is the pseudopolynomial part, is just 0 to 200, I think, or 100 maybe, yeah, or 1 to 100 to be more precise. And this is, I guess, 1 to 200 actually, not 0. Didn't we look at it? But well, the input to this could be 0, I guess, but yeah, roughly speaking, right? So the number of total possible inputs is just 20,000, as we talked about, which is n times, which is O of n times, forget the notation, but like, you know, let's just say C, where C is, you know, do they have a variable name for it? No, they didn't name it, that's why. So let's just say C is the possible input to this, right? And oh wait, sorry, I think I messed up on this one. Actually, the total left is, I actually messed up on that, so my bad. But yeah, so total left is actually the sum divided by 2, right? So it is actually, the total sum can go up to 200, is 20,000, and then divided by 2 is just 10,000, right? So this is going to be from 1 to 10,000. So very naively, this is about, yeah, n time n squared times c, right? Roughly speaking, and each of these will do all of one operation. So that is, each core does about all of one of work, because all of this is just all of one because we assume that these are cached already, right? So therefore, total cost is equal to O of n squared times c, right? And that's not a tight bound. And what I mean by that is that a lot of the reason why we do it top down in a way is that a lot of these states are not possible. And what do I mean by that, right? What I mean by that is that, for example, let's say you have an array of 100, 100, 100, 100, 100. Let's just say 5 100s, right? Let's say that's your input array. Well, half of the, let's just add one more for even number. So the sum of this is just 600, right? And half of this is 300, obviously. But so then the first input to this is going to be, say, 0, 300 is going to be the first input. But a lot of these states are not possible, right? Because you cannot get to 0 to 99, you cannot get to 0 to 98, you cannot get to 0 to 97, and so forth. And also a lot of the negative numbers, and even because you can only you cannot get to indexes to these numbers, but also even just that aside, with respect to, because these are hundreds and 299s are not happening, you cannot even get to, say, 100, because you know that the max number is going to be 100. given constraints. So no matter what the property of the numbers are, even in the worst case, this can only be from 200 to 300, right? So I'm saying that from the top-down perspective, a lot of these states are not possible. So that's why that, even though this is the worst case analysis, the actual running time will be way better. Yeah. Okay. So given said that, let me hit the submit button, because I think one time recently I explained the problem on stream and then I forgot to hit the submit button. So I actually end up submitting that problem late. So that was a little bit sad. Oh no, memory exceeded. Okay. So that is something that I thought about and was worried, which is what we talked about, because it contains 2 million elements up to, which maybe is cutting it close. To be honest, I thought it would still be good enough. But let me click on more details to see. Okay. Well, so we passed all the test cases, but it took too much memory. Okay. So I think another way to solve this is just using LRU cache. I think that should be good enough, to be honest. The way that I did it is very inefficient. I just kind of put in a thingy. There are libraries that let you do this in a more optimized kind of way in terms of storing these things. And I was kind of lazy because I used a thing instead. That's what I get for being lazy. So let's actually convert this to let's convert this to an array or a matrix, but that will only be even more. So okay, so then now I guess you get the benefit of me trying to now convert this to dynamic programming. So now we have all this code. It's too slow because it takes too much space, so we have to convert this to, well, dynamic programming, right? So we're going to do that. Let's just call it DP just by convention. Let's just start everything with force. And now we're going to construct the states, right? What do the states look like? As we said, we have index, which goes to 1 from 200, and then total left, which is 1 from 1 to 10,000. So let's do it that way. The inner loop, say, is going to be total half plus 1, I guess. And then we do this for range is equal to n plus 1. So we have this array. Yeah. And we'll go over this again, so I could delete it. Okay, so then now, what are our base cases, right? Base cases are 0, 0 is equal to true, because that means that if the number left is 0, is possible, and also if we use 0 numbers, that's going to be true, right? That means that we're able to reach that. And then now, for index in range sub n, so we just go through each number, and what do we do for each number, right? Well, we go from, for k is in range of total half plus 1, maybe, I think. Yeah, maybe that's okay. dp sub index to k is equal to, I actually have a video that goes over the progression of how to go from top down to bottoms up, and then from bottoms up to the space optimization. I might do the space optimization here if it becomes troubling again, but in terms of transitions, we'll go over it a little bit. But this is the only base case you need if you handle your if statements right. So what happens with this index? Well, actually, this should be. I like to do it this way, so that we leave 0 for 0 items here. So DP gives us the answer for after using. So the definition is slightly different just for implementation purposes. So DP of x, or let's just say index of k, is equal to whether it is possible to sum to k after using index elements. Right, so after using 0 elements, we can reach the sum of 0. So yeah, and here, and you have two choices. You could either push forward or pull back. I'm going to try the pull back method, and what I mean by that is that for each number, let's say if dp of if k is greater than or equal to num sub index minus 1. then dp sub k is equal to dp index minus 1 k minus number sub index minus 1, right? And I'm not going to go over the transition that deeply because we kind of talk about it in the top-down version. And noting this, by the way, this statement is true only if we start from the for loop. So we could actually just go directly put this in the for loop. And yeah, and then at the very end, we can just return db n and total half. So let's give that a go. Huh? Why didn't my oh, because I clicked on some stuff. That's a little bit sad. All right, let's just run it for these, and then we'll construct more if it works. Okay, so this is false. Whoops. So I probably have something off by 1 somewhere. Oh, this is not just equal to, it is an or equal to, right? So if this is already true, you don't set it to the false null value. So that's at least one issue, but there's apparently even other issues. So, well, for this, it's easier to just print the DP array. That's why bottoms up is slightly easier to debug. Yeah, so and the source one is true. After one number, okay, so I see what I did by accident. What happens is that I only use this number, but I don't do the instance where it doesn't use this number, right? So I think I tried to do a little bit shortcut and failed, but we can actually fix this. And what does that mean is that we want to handle the not using this number case. So this has to start from 0. And how am I able to debug this so quickly? Well, some of it is just experience, and because I messed this up before in a similar way. And this is this should solve it. But looking at it, yeah, and that's just practice, right? There's no, I don't really have anything simple. It's just practice and being familiar with it. You can see that this is actually already faster than when we had it before, but let's kind of see it a little bit. And also I want to do a case where it's just 100 because I think that was the issue with the memory before. So you definitely want to test, you know, the stuff that you have issues with. So this is 10. How many numbers are there? 200. Okay, so it's still a little bit slow, but you know, at least it handles the space. And here, I think what I want to do now is kind of figure out, and there's some optimization you could do for the speed. And I'm going to submit this to see if it runs the space complexity, and we'll see. Ooh, is it going to give me another memory limit issue? Okay. Let me just click on details since I am curious about the memory usage. So the memory usage is 29 megs, which is good enough. I mean, it's a little bit slower because I could have done some space usage. Because you can definitely make it, yeah. I have like I said, I'll link a video below on how to make this progression to change it into more space efficient. It's actually really easy, but I don't want to go over it right now in this video. Definitely upsolve it and practice that. Let me know what you think. Hit the like button to subscribe. Oh wait, I have to go over the complexity. We kind of go over the complexity with respect to top down. So now this is bottoms up. The complexity is actually the same. But because when we used the map, which was, to be honest, because I was a little bit lazy, there are overhead to the cost, and that's why it makes the space complexity, or the space complexity is the same, but you know, the constants matter sometimes, and in this case it does. But here, we can see that, you know, in space, we literally have a 2-dimensional array, so it's just going to be n times total half, which, as we mentioned, is going to be n times c roughly, so n squared over c, and because we look at each cell once, you know, that is the cost of the time as well. And for space, as I mentioned, you can actually reduce this to just n times c, which is the pseudopolynomial part, which is this times that. You know, you can watch the video that I'll link below to get to that. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and I will see y'all later. Bye bye.